Let's take a look at this example here, the integral from 1 up to infinity of 1 over t squared dt. So we're going to a purely geometric question here. So if we have the integral, the first thing you must do is apply that definition of improper integrals. You cannot sub in infinities into anything. You can't do it. So we have to sneak up on that infinity by saying, no, I don't really want to integrate to infinity. I want to integrate to some upper limit. Let's call it, we can call it capital T, but we have T's everywhere. Another letter name that's often used is B for upper limits, like A to B. And we're going to do exactly the same integral. That stays the same. So the idea is we're not going to integrate all the way to infinity at once. We're just going to integrate from 1 to some other fixed number. And then once we've done that, we're going to let that upper limit push its way out towards infinity. Okay. And the idea is that this is now going to be finite and well-defined. Okay. So if that procedure makes sense, then the next challenge is simply to evaluate this integral. So what we're going to have to do a whole bunch of times here is just copy this over. Copy this limit as b goes to infinity. That'll be the very last thing that we apply. So it just stays around when we're talking about these equal signs. We have the integral of t to the negative 2. That's a much better way to write 1 over t squared when we're doing integration. We're going to add 1 to the power, divide by the new power, and evaluate that from between, at b and at 1. And so we're going to copy again. We're going to have our limit as b goes to infinity of negative 1 over, plug in the b, t to the negative 1 is in the bottom, the negative 1 can be out front, minus negative 1 over 1 from the 1 value here. Okay, if we do that, then now we're actually in pretty good shape. I'll copy the limit one more time just to tidy up first. This is plus 1, so it'll be 1 plus 1 there, minus 1 over b. And now we're ready to ask the question, what happens as b gets larger and larger? Before we evaluate that, let's make clear what's happened. We have our graph of 1 over t squared. We have the lower limit of 1. And we have the limit of b. What this calculation here says is that this area is equal to 1 minus 1 over b. So whatever b is, this area underneath it, underneath the graph of, what's the graph of? The graph is 1 over t squared. So the area underneath the graph of 1 over t squared from 1 up to b is going to be the integral that we calculated, 1 minus 1 over b. What happens then is we take this upper limit, we push it further and further out. Well, b gets bigger and bigger and bigger. If b gets bigger and bigger, then the overall value of 1 over that is going to go to 0, and so we get 1. This is a nice finite number. Not that infinite ones are not nice, but this is a nice finite number. And we would then say, if we wanted to, if someone asked us to phrase it this way, we would say the integral converges. We got a nice value, so this integral converges. Let's take a look at a contrasting example to see how it might work out a little differently. We're going to compute the integral, the improper integral of 1 over t from 1 to infinity. And again, first step, mandatory, no option, marks lost, the whole thing, is to apply the definition. Sorry, I'll sneak up on it. We want the integral from 1 to infinity, but we can't have that all at once. So we're going to integrate from 1 up to some other number, keep everything else the same, but we're going to integrate up to a fixed number, and then afterwards, we're going to see what happens when we let our limit up there get larger and larger. Okay. Now this one is a little easier, in fact, than the other integral in some ways. Don't forget, copy this limit as b goes to infinity. It's the last thing we're going to use. But what do I differentiate to get 1 over t? This is, remember, the one exceptional power rule. Ln of absolute value of t is what we get here, b and 1. So we anti-differentiate, and then we plug in these two values, copy again, The limit gets copied. We still haven't handled it yet, so it has to stick around. But we can plug in the upper limit. B is positive, so that's fine. We can take away the absolute values. Ln of 1, 1, and absolute value of 1 are the same. That's actually 0. Okay, so we now have an expression that's much simpler than the original integral. We can now evaluate it and ask what happens to ln of b as b gets larger and larger and larger. Here you have to know your graphs. Remember, ln is that function that does this, and one of its properties is that as you go out to infinity in the x direction, ln of that value gets larger and larger and larger. So actually this does not equal something, but heads off to infinity as well. As b gets larger, ln of b goes off to infinity. So we would say that this integral diverges, because this is not a finite value in the limit. And that contrasts with our earlier example. We'll just flip back for a second. If we had the integral of 1 over t squared, then we did our calculations, evaluated the limit. The b showed up in this particular form here. As b got larger, we ended up with a limit that was just 1. That was great. We had a converging integral. When we look at the 1 over t, we see something different happening. We get b showing up in a different place, and when we let b get larger and larger, then we do not get that converging to a finite number, and so we get a divergent integral. And what that means is we're talking about the areas under graph. Here it actually goes off to infinity. Now it's worth at least looking at the graphs here for a brief instant. And if we look at these graphs, sorry, let's do that. There we go. If we look at the graphs of 1 over t squared, let's make that 1. And the graph of 1 over t, if that's 1 and that's 1. 1 over t would go down to a half, then down to a third, then down to a quarter, and has an asymptote. That's fine. That's the graph of 1 over t with t, and we're talking about that area underneath that graph. And we'd say that this is infinitely large, infinite area, when we head out towards as large a upper boundary as we care to look at. Compare that to 1 over t squared. So for 2, we're down at a quarter, then an eighth, and then a 16th, or a ninth and a 16th, sorry. This is the graph of y equals 1 over t squared. And this area, even when we push the boundaries out, is going to equal exactly 1 square unit. Okay, let's take a look at these two graphs and ask the question, how much does graph sketching help us when we're trying to analyze these scenarios? This area under this sketched graph is finite, it's 1. The area underneath this graph as you go out to infinity is not 1. It's in fact infinitely large. I defy anyone, quite frankly, to look at this graph versus this graph and say, oh yeah, this one diverges, this one's okay, it converges. You can't tell much from the graphs. Both of these graphs have basically the same shape, and it turns out the devil really is in the details when you look at what happens to these functions as x, or t in this case here, gets larger and larger. So graph sketching really doesn't tell us much, if anything at all, about the area underneath these graphs as we go out to infinity. We can estimate for finite intervals, but by including this infinite upper bound on the integral, we get into really interesting territory intellectually, but really frustrating territory if we're trying to rely on graphs to help us out here. That being said, we should make one comment, which is, if the graph didn't go down towards 0, like if it kind of went up and bounced around, then it's very clear in these scenarios that this would be infinite area. The only cases we're really going to struggle with are when the graph goes down to 0, so there's something getting smaller, but the area gets larger because we're having an infinite area, infinite axis side, and so there's some kind of 0 versus infinity battle going on here, and we're trying to figure out under different conditions, which one of these values is dominant. Do we get a finite mixture of this zero graph, or does the infinity of the x-axis interval, t-axis interval dominate and we get an infinite area? That's what we're going to look at in more detail.